Imagine a universe where reality constantly shifts, a cosmic dance of possibilities collapsing into concrete existence. What if our very act of observation, the way we interact with the world, isn't just a passive viewing, but a participatory act, a force shaping the universe itself? This is the captivating mystery that quantum mechanics, the science of the very small, presents us with. For centuries we've clung to the comforting notion of a clockwork universe, predictable and absolute. Yet as we delve deeper into the subatomic realm, a stranger, more counterintuitive picture emerged. Here, particles exist in a haze of probability, their fates uncertain until the moment of observation. This is where the intrigue of objective collapse theories comes in, daring to suggest that the universe might have a way of collapsing these possibilities on its own, independent of us. This journey takes us beyond the familiar, challenging us to rethink the very fabric of reality. It compels us to ask, does the universe possess an inherent tendency towards self-definition? Or is our role as observers more crucial than we ever imagined?
To grasp the essence of objective collapse, we must first venture into the heart of quantum mechanics. Picture a world where a single particle can be in multiple states at once, a concept known as superposition. It's like a coin spinning in the air, existing as both heads and tails simultaneously until the moment it lands. In the quantum realm, observation acts as this landing force, forcing the particle to choose a definite state. This is the perplexing phenomenon that has baffled physicists for decades. It's as if the act of looking somehow influences the outcome, blurring the line between observer and observed. This inherent ambiguity is where interpretations of quantum mechanics diverge. Some, like the Copenhagen interpretation, argue that it's not our place to question what happens before observation. Others, like the many worlds interpretation, propose that every possible outcome actually occurs, branching off into separate universes. Objective collapse theories, however, offer a bolder proposition, that the collapse of superposition is an objective process, driven by a fundamental mechanism within the universe itself. It's a radical shift in perspective, suggesting that the universe might be far less reliant on our conscious observation than we previously thought.
Imagine a cosmic rulebook hidden within the fabric of reality, dictating when and how quantum possibilities crystallize into actuality. This, in essence, is the core idea behind objective collapse theories. Instead of relying on an observer, these theories propose that the collapse of the wave function, the mathematical description of a particle's state, happens spontaneously, governed by specific physical laws. Think of it like a soap bubble. It exists in a delicate, shimmering state until a slight disturbance, a breath of air or a touch, causes it to pop. Similarly, objective collapse theories suggest that quantum superpositions are inherently unstable, prone to collapsing into definite states over time. The universe in this sense becomes an active participant, constantly shaping its own reality. This spontaneous collapse, however, isn't random. Different objective collapse models propose specific triggers, often linked to gravity or modifications to the Schrödinger equation, the fundamental equation governing quantum systems. These triggers act as thresholds, beyond which the superposition can no longer hold, forcing the quantum system to choose a single definite state, definite.
Within the realm of objective collapse theories, several models attempt to pinpoint the exact mechanism driving this spontaneous reduction of the wave function. Two prominent contenders are the Ghirardi-Rimini-Weber (GRW) theory and Roger Penrose's model, each offering a unique perspective on how the universe might be self-collapsing. The GRW theory, named after its proponents, suggests that spontaneous collapses occur randomly in time and space, affecting individual particles. Imagine a cosmic lottery, where each particle has a minuscule chance of collapsing at any given moment. While the probability for a single particle is small, the sheer number of particles in the universe ensures that collapses are constantly occurring, shaping the reality we observe.
Penrose, on the other hand, proposes a more elegant connection between gravity and quantum collapse. He argues that the curvature of space-time itself, as described by Einstein's general relativity, could reach a critical point where it forces the collapse of superpositions. Think of a tablecloth being pulled taut. Eventually, the tension becomes too great, and the fabric tears. These are just two examples of how objective collapse theories attempt to bridge the gap between the counterintuitive world of quantum mechanics and our everyday experience of a definite reality. While the precise mechanism remains a subject of ongoing research, the core idea that the universe has an inherent tendency towards self-definition offers a compelling alternative to observer-dependent interpretations.